So last week we talked about natural transformations between functors. And I said this week we would do adjoint functors. But in order to construct many of the interesting examples of adjoint functors, we need limits or colimits. So I decided today to talk about limits and colimits. And we could have given examples of these before without the formal definition. So I'll start by doing that. So the idea is that many objects in mathematics are characterized by some property, formulated in terms of how you map into it or how you map out of it. So let me give a bunch of examples which I hope are familiar. The first example is distinctly. Yes, I will try. Please remind me. So let me start with an example. If x and y are sets, then you know what their product or Cartesian product is as a set. Is the set of pairs, one from x and one from y. And this product comes with two maps, projection to the x factor and projection to the y factor, which I'll call maybe pi x and pi y. And if I have a third set, and I want to define a map from z into x cross y, suppose I have one, I can compose it along the two projections and get two components. I'll call that px and py. So this is some map. Let's call it big F. And note that F is just big F followed by px cross big F followed by py, where the cross means it takes an element of z and gives me a pair. Evaluate this on little z and evaluate this on little z. So to give a map to the product is the same as to give a map to each component or each factor. And this is a fact so familiar that you probably never think about it explicitly. And this characterizes the product as a set up to isomorphism. Up to a unique isomorphism. Namely, if I have some other set, so given a set W with maps I don't know, let me call it pi prime x to x pi prime to y such that maps of sets from Z into W are the same as just what you get by looking at the two components composed. So this takes what? This takes a map F to the two components. So if W is a set with two maps like this satisfying this property so that I know how to map into it by just mapping into the components, then there's a unique map from W into the product. It's just given by these two maps. And it's an isomorphism. The fact that it's an isomorphism follows from this. So you can write down the map in the inverse direction using this. So let Z equals x cross y, put the two projections here, pi x and pi y, and you'll find a map from x cross y to W, which is inverse to this one. So the product is characterized by this property of having two maps out of it, and any other map into it is characterized by its projections onto those other two pieces. And more generally, given many sets, xi, we can form the product over an indexed set. So this might be infinite. It's a set of infinite tuples. And this is characterized by having a bunch of projection maps onto each factor. And maps into it are determined by the components. You could also take an empty product, a product over an empty collection. So if the index set is empty, then the product is not empty because you need to be able to map to it according to this property. The product is a one-point set. So it's the empty tuple. It's the set consisting of the empty tuple. Okay, and you can do something similar in the category of topological spaces. You should remember from topology that if you have two topological spaces, you can form their product. There are many topologies you might put on it, but there's one called the product topology. And why is it the good topology? If x and y are topological spaces, the product topology has a basis of open sets of the form u cross y and x cross v. Then you can take intersections and finite intersections and infinite unions of those. You get a topology. So by construction, that's what the product topology is. But what is it sort of by definition? What characterizes it? So with respect to this, the projection maps to the two factors these are both continuous. That's why these have to be open, right? If I have an open subset X and U and I take its preimage, this is what I get. So this has to be open if I want the projection to be continuous. And similarly here. So the projection maps are continuous. And to give a continuous map from another topological space to X cross Y is the same as to give continuous maps to each component. Okay, so that's just like this. That actually characterizes the product as a topological space up to homeomorphism. It's just like this, except now the maps for which it should satisfy this property are maps in a particular category, namely topological spaces, not just set maps. Yes, it's the same thing as here, but put top instead of set. And we're going to formalize.
Is it really the same as defining the topology as product topology?
Yes.
So it's enough.
So this characterizes X cross Y up to homeomorphism, and similarly for the infinite product. On the infinite product, people often put various topologies. But the product topology is the one with this property. Okay, so that's about how to map two things and how to characterize objects for which you know how to map to them. There's a dual notion of mapping out of things. I could have taken the disjoint union of sets. Actually, before I do that, let me give a little more general example, because I need all the following kinds of examples. So given a diagram of sets, suppose I have a set X, which maps to a set Z, and Y also maps to it, F and G. The fiber product, you may or may not have seen this before. The fiber product as a set is constructed. So this doesn't characterize it. This is just the construction, and then we'll characterize it. So the notation is X cross Y over Z. So the map from X to Z and Y to Z is implicit in the notation. This is constructed as a subset of the product of X and Y. It's not all tuples. It's those tuples such that the image of X equals the image of Y. So if Z is just a one-point set, that's always true. Every image is just the given point. But in general, this is different. So example, special case. Special case would be X is a point. And then what is this? Well, there's only one thing I can put here for little x, whatever its image is. It maps to something in here, little z. And then the condition on y is that g of y equals that given little z. Здесь нет композиции. I didn't understand the question, maybe.
I said that we can
Okay, so whatever the image of f is some little point in big Z. And this fiber product is just the preimage of little z. Under G. So this is the fiber of G over the point little z. So it's called the fiber product because of this fact. So it's kind of a family of fibers, if you like. And one more kind of example that's kind of similar. So you could also have done this in topological spaces. I didn't finish characterizing it. Let me give the characterization. So note, there are also projections here. It's just a subset of the product in this case. So we have projections. And to give a map into the fiber product, not just projections, actually. We do have projections, but let me draw them like this. They're not just projections, but if I go around this square in the two different directions, it commutes. I could go around this side or that side, and I get the same map from the fiber product to Z by definition, or by construction. So we get projections forming a commutative square. And to give a map into the fiber product, it's to give a map to x and a map to y such that the composites give the same map to z. So it's to give such a commutative square. So f and g are fixed. This is data that I have to provide, the maps to x and y, and there's a condition, which is that the two composites are the same. So this is forming a commutative square. And then, if you take these two components and use it to define a map to x cross y, it will land in this subset of the fiber product by this condition. Okay? And using that property to define maps backwards, you can see this characterizes the fiber product up to unique isomorphism. So I'll just remark you could do the same in top, where you give this subset the subspace topology. In the product. Who has seen fiber products before? Okay. Here's another kind of example. It'll be defined as a subset satisfying some conditions, constructed as. So given two maps, from X to Y, same source and same target, but two different maps. Given two maps, their equalizer by construction, and then we'll give the property characterizing the construction. So the equalizer of F and G, it's a subset of X. It's the points in X where F and G, so these are two maps of sets. So by construction is this. It's the set of points where F and G are the same, where F and G are equal. It could be empty. F and G could be totally different, and they don't agree anywhere, or maybe they agree somewhere, and then that's a subset of X. Okay, and this is characterized. So to give a map to the equalizer, well, if I had a map to the equalizer, I could compose it with the inclusion into X. So I would get a map to X. And then when I compose further with F and with G, the two composites would have to be equal. And that characterizes the map. So to give a map to the equalizer is to give a map, let's call it big F, to X, such that the two composites are equal. If that's true, then the map W will factor through this subset, the equalizer, and conversely. So that characterizes the equalizer up to isomorphism. It's some set with a map to X such that the two composites are equal. And to give a map to it is to give a map to X with those properties. So any other one factors through this one. Okay, very good. So any questions about these examples before we do the dual examples?
I just don't understand. There is from double V to X, and it's saying that if little f big is g little f big, but looks like we define not only the map to the equalizer, but to the whole X.
Yes, but I'm claiming that any such map to X with these properties lands in this subset of X.
You mean that it can't be solved with
The image of big F lands in the subset.
no, and so we can map this F anywhere other than to the equalizer.
Mm-hmm.
Okay.
Okay, so now dual examples. Instead of products, we could look at disjoint unions. We have the disjoint union. So when it's really disjoint, they're not union of two subsets in an ambient set, but they're just two sets, X and Y, that have nothing to do with each other. I want to form the disjoint union as a new set. So the disjoint union of sets, this has what? This has two inclusion maps coming into it. let me call it Ix and Iy. And to give a map out of a disjoint union, not to, but out of a disjoint union, is to give a map out of each component. If I put all the stuff in x in one hand and all the stuff in y in the other, and they don't intersect, and I want to give a map out of both hands, I just tell you where this goes and where this goes. And this characterizes the disjoint union up to isomorphism. This example is almost a little too obvious. It's kind of so easy it's hard. I'll give other examples of something characterized by the same properties, but where in some sense the two things are not really disjoint. They're going to meet somewhere. Likewise, you can do this for topological spaces. The two inclusions, if I take a disjoint union of topological spaces, so for topological spaces, the inclusions are continuous. And to give a continuous map out is give a continuous map out of each component. And then we had pull back or fiber product. So now I want to give the dual notion. So instead of drawing a diagram like that with two things coming in, I'm going to draw a diagram like this with two things coming out. So given maps of sets, from Z to X and Y, I'm going to call these again I, but they're not necessarily inclusions, they're any maps. So given maps of sets like this, the push out so remember the fiber product was constructed as a subset of the product. The push out is going to be constructed as a quotient by an equivalence relation of the disjoint union. So this is a quotient. So let me give the notation. The push out is denoted X cup over Z Y. So this is constructed as I form the disjoint union, and then I impose an equivalence relation where X is equivalent to Y if they're both in the image of the same point. So if there exists a Z such that Ix of Z equals I y of z. So you should think of this diagram as instructions about how to glue a piece of x onto a piece of y. You glue them together where z tells you to glue them together. And you do this a lot in topology.
Maybe you just wrote something because
What's that?
because what you have wrote is similar to the fiber product, but it should be Ix of z equals x, y z equals y.
I said there exists.
Yeah, but what you have wrote, it doesn't mention any x or y. So how can we build a relation?
Ah, sorry.
Yeah.
Sorry. Thank you. So this equals x, indeed. And this equals y. So little z is and together with these maps is the instructions that little x should get glued onto little y. And you do this a lot in topology. You've seen it even if you didn't recognize it as such. One of the most common constructions of interesting topological spaces is exactly like this, where you put the quotient topology on here. So let me give a very specific example. In topological spaces, if I take 2 points, that's a discrete space, included into an interval, and I map also to a single point. So this is my z, this is interval, this is point, so this is supposed to be x, this is supposed to be y, then I could form this set, this push-out set. What would I do? The only 2 points in this disjoint union that get identified are this one gets identified with this one, because this maps to this, and maps to here, and this also gets identified with that, because this maps to here and to here. Okay. So as a set, it just looks like the interval with the 2 ends glued together. And the quotient topology I should have told you what characterizes this, so I'll go back in a second. So the quotient topology is the topology on this push-out for which, so let me go back here. We need to fill this in. I should have told you what the characterizing property is here. So to define a map out of this push-out, is to do what? Is to define a map out of each of x and y which agrees on z. So let me draw it. So if I have a map of sets like this, this is the same as to define 2 maps, one out of x, one out of y. Such that they agree on z. So I can precompose this with the map coming from z, and that should be the same as precomposing the map out of y with the map coming in from z. Okay, so you can check the formula does that, and that characterizes the maps. And it's the same here, except everything should be continuous. So for which continuous maps out of the push out are as for sets, but continuous. And finally, we have the dual notion for co-equalizer. So given two maps of sets, the co-equalizer is constructed as it's a quotient of y it's the quotient y by some equivalence relation where y is equivalent to y prime if what? There exists x there exists x such that f of x equals y, g of x equals y prime. And then to give a map out, is that correct? That looks like the push out for what I've written. Just a sec. That is the push out, and I think this is the same. Yeah, that's right. So what I wrote is the push out, not the co-equalizer. So this would be the push out where x and y are both y and z is equal to x. So what I want to say actually is, where the only things that get identified are the image, they're both the image of the same element of x. So then, how do we map out of such a thing? Respecting this equivalence relation, there's a single little x. So I have two different maps from big X. And so I can look at the image for any given little x. I can look at its image under F and its image under G.
Could you draw the same diagram as there?
This is the diagram. This is the correct diagram like this. It's not like this, it's like this. And so let's think about how to map out of this equivalence relation. Or maybe we do a very explicit example. Let's do an explicit example. Special case. Special case. Suppose x is just a single point. Okay? And suppose y is 2 points. Let's call them y1 and y2. And let's call this consists of a single point. And suppose f and g are such that f of x equals y1 and g of x equals y2. Then the equivalence relation is telling me y1 and y2 should become equal. So that's what it means. Okay, right. So then I map out of the co-equalizer so notice by construction it's y quotient and equivalence relation. Yes. Well, here it's not a push out. It's a different quotient. It's a quotient of y, not a quotient of x disjoint union y. And the role of z, if you like, is being played by x. X, together with the maps into y, are providing the datum of the equivalence relation that we impose. In this diagram is different because z, together with its maps to x and y, are providing that data. It's not a push out. It's a different construction. Okay, so then a map out of this co-equalizer. Note that by construction, the co-equalizer was given as quotient by an equivalence relation, so it has a map from y. So a map out of here is the same as a map out of y that respects the equivalence relation. And another way to say that is it's a map out of y so that when I precompose with the two maps f and g, they become the same. Okay, so that is, it's a map from y to some w such that, precomposing now with little f, same as precomposing with little g. And you can do similarly in topological spaces. You just have to put the quotient topology on this. So likewise, for in topological spaces, using the quotient topology. So whatever the quotient topology is defined exactly so that you know how to map out of a quotient by an equivalence relation with the quotient topology. You just have to make everything continuous. Okay, and we'll do lots more examples of this in the seminar. Yes?
When you gave the first example of
yes.
product, you have instantly generalized it for the case of infinitely many
yes.
vectors. But in the following examples, we are talking about two objects.
Yeah, there's no particular reason. I could have, when I talked about the disjoint union, I could take the disjoint union of infinitely many objects. Yeah, that's fine. Any other questions about the examples? Pardon? No, I don't. Is it? Let's see. Where did I put it? Here it is. sorry, the question is an equalizer a fiber product? So let's see. So by the way we constructed it, it appears as a subset of X. If I form the fiber product like this, what is this? This is x1, x2, such that f of x1 equals g of x2. Whereas this is a single x, such that f of x equals g of x. So these are different, because here I don't require that x1 equals x2. So what I could do is I could take this as a subset of x cross x and intersect with the diagonal where x1 equals x2. But in general, they're different. Any other questions before we give a general definition? Okay. So all of these are examples of very general constructions where we characterize objects and maps into them or maps out of them in terms of some properties. So I need to give some language in order to formulate the definition. So definition, given a small category, small means there's a set of objects. You can fuss about set theory if you want to. I don't want to, so I'm going to assume it's small. So given a small category I, a diagram and a category C, maybe C is big. There's no set of all sets. A diagram of shape I is a functor from I to C. Okay? So I could have just called it a functor, but I want to emphasize that I'm thinking of I as a kind of shape inside C. So what does that mean? For each object, we have an object of C corresponding to it. This is a single phrase. This is the thing I'm defining. The thing in quotation marks is what I'm defining right now. So shape doesn't have an independent meaning. So we have an object Fi and C, and for each arrow or map inside I, we get an arrow in C between the image of I and the image of J. And this is compatible with composites and identities because it's a functor. So what are some typical small categories I for which we consider diagrams? I might be the category with a single object and a single identity morphism. And so to give a functor from that is just to give an object. It could be a category with two objects, let's call them 0 and 1 just to have names for them, and two non-identity morphisms between them. So when we were talking about equalizers and co-equalizers, we were actually given functors out of that category. We give two objects, x and y, the image of 0 and 1, and two morphisms. You have some diagram like this. But the definition is very general. Well, how do I give a functor out of this category? I have to tell you where the objects go. So I have to give you two objects, x and y. And I have to give you two maps between them, little f and little g. So a functor out of this diagram is exactly the same as this data that we wrote. So in this example, it was sets or topological spaces, but it could have been anything. If x and y are sets, then it's sets. If x and y are groups, then it's groups, and I would require little f and little g to be homomorphisms. Okay. Sure. So let me give an example of the last sort. So a functor, let's do a very explicit example. Suppose I have infinite dimensional, so a space of sequences. Let me write it like this. So we have a sequence of spaces and continuous maps. Like this would be a functor out of n. And the way such things arise in practice, for instance, you might be trying to understand some infinite dimensional topological space and write it as a union of finite dimensional subspaces. So very explicitly, you might have zero, the zero-dimensional real vector space, Euclidean space. And then you might include this as, I don't know, the first coordinate. And then this is the first two coordinates. And so on. Okay, and then taking the union, you'll get an infinite dimensional topological space. Or, more interesting, this is how you study the infinite dimensional complex projective space, or real projective space. So these are classifying spaces that appear in topology, and they come with a natural sequence of subspaces like this. We'll give more examples in the seminar where you have not just a sequence, but a whole poset of subs.
So the founder of the exercise is a diagram of shape I.
Yes, where I equals n. That's what's happening in this example.
Is it unique?
No, because I could change the objects. I could change the maps between the objects. I just gave two different examples. Okay, so note diagrams of shape I in C they form a category in which the maps are natural transformations. No. This is if you take the limit over all of them. It's not a member of the sequence. It's actually the co-limit, and we're going to define that. So yeah, this is kind of a dot, dot, dot that goes off to infinity. Okay. So let me write it not on the same line, but all of them are including into this common thing. So where the maps are natural transformations. Yes. And concretely, what does that mean? It's kind of a map of diagrams in a fairly obvious way. So concretely, so for example, given diagrams, let's say, it's just in some category, it doesn't matter which. I'm given one diagram and a second diagram. A map between them is a map from x to x prime and a map from y to y prime. Let me call it alpha x. This is the component of the natural transformation. Maybe call it alpha 0 and alpha 1 because it corresponded to 0 and 1 here. Such that f alpha 1 equals alpha 0 f prime and g alpha 1 equals alpha 0 g prime. Okay, so that's what a natural transformation would be, but thought of as a map between these two diagrams. And if you imagine a more complicated diagram, it would be maps between each object that appears in the diagram commuting with all the maps. And note, among all diagrams, there's some special ones that are very, very simple. So given an object, just pick an object, any object in C. Let's call it little x. So given any object, little x in C, I can form a constant diagram. I'll write it as x underline. It sends I, every object, to the same object, x. And it sends every map in I, every arrow in I, to the same map here, namely the identity map. Okay, so it's a very stupid looking diagram. You just collapse everything to a single point in the category C. Okay? And then, by definition, I have to remember who's cone and who's cocone. Just a minute. I screwed this up when I was writing my notes and had to look it up. All right. So a cone in, how do I want to say this? Okay, I want to say it like this. So given a diagram, I to C, a cone for F is a map of diagrams from some constant diagram. So let me draw what this looks like, so you can see why it's called a cone. So that is, how do I give this map? I have the constant diagram. So for all objects I, we have a map I'm not sure what I should call it. It's a natural transformation. And here's an example.
And when you say a diagram, then we mean as a functor that is constructed.
So what is a map from the constant diagram to F? For each object I, we have a map from the object X to the object F of I. I have to give that a name. It doesn't matter too much what I call it, I guess. Maybe I'll call it pi I. And such that for all maps in I, the following diagram commutes. So I have X, I have its map to F of I have its map to F of J. It's an object. takes values, namely C. So it's an object in C. Okay, so this should commute. In other words, pi I followed by the value of the functor on the arrow is the same as pi j. Okay, so it's called a cone because of this shape. So you have x up here, and then you have fi mapping to fj, mapping to fk, mapping to something else. So you have some big complicated diagram of objects and arrows, and x is mapping to all of them and commuting with all of these arrows. So this shape is a cone. And a cocone is just it's a natural transformation from the constant functor to f. And x can vary, so there are many cones, many potential cones. So let's give an example.
So the neutrality of the transformation is given by, is described extensively
The fact that this diagram commutes is the naturality. So if you like, I could have drawn this instead as x. Here, this is what the constant functor does to f, but that's just the identity.
But here the identity, I thought that we could rotate the diagram clockwise, but then the arrows would be from right to left, and there they are from the left to the right.
It doesn't change anything. The definition, well, I'm not sure what you mean by rotate, but I could draw it like this, where x is on this side mapping to the values of f. This is what it is. Let me give an example. This will illustrate it. Okay? So let's let I be this. So this was the kind of diagram that we considered when we did pullbacks, right? So let's fix a diagram of sets or topological spaces or anywhere it makes sense. It doesn't matter. Okay. Then what is a cone? Then a cone over this diagram it's some other object. I was calling it W in the examples, but let's call it little x, different from big X. It's an object little x with maps from little x to y and to z, such that all the composites are the same. Sorry, what's the question? Well, how do I specify a constant functor? I just specify an object. There's no other data. So specifying the constant object is just picking, a constant functor is picking an object. I pick the object. Then I provide a bunch of maps that commute in some way. That's the data of the natural transformation. Yes. There's neither more nor less data in a constant diagram than the choice of an object. That is correct. Okay, so cocone is a dual thing. So given now, so dually, a cocone under F is a map of diagrams to a constant diagram. And so it looks very similar, except now I have a bunch of data like this. So for each I have a map from f of I to my given object, which specifies the constant functor. I'll write this as I sub I sub j, like this. This is ff, and this all commutes. It's called a cocone under because it looks like the cone but upside down, or with all the arrows reversed, rather. Okay? Making them what? Not yet. Not yet. Very soon. So there are lots of cones and cocones. They're not unique, but those which are special are going to be limits and colimits. Okay, so I should have done one more example. We could have done this on the first day. So maybe let me give definition. In a category, an object let's say X is final if for any other object there's a unique map to this one. So everything ends there. So for instance, in the category of sets, I could take the one-point set, everything unique maps uniquely to the one-point set, just the constant map. Similarly in topological spaces. The object is initial if for all other objects there's a unique map from X into Y. So in the category of sets, I could take the empty set. The empty set maps uniquely to any other set because there's nothing to specify. Okay, so definition. Given a diagram of shape I and C, a limit, so I should make a remark. You can easily check if final or initial objects exist, they're unique up to isomorphism. Then they're unique, up to unique isomorphism. So this is easy to check. If there is one, then any other one maps to it, and conversely. And that map is unique. So the composite of the two must be the identity. So given a diagram, a limit of f, if it exists, sometimes it does, sometimes it doesn't. This is a what? A final cone. all other cones over F map to it. It's denoted, when it exists, it's denoted as lim F over I. Okay. So let's look at our examples. What does this really mean? Let's kind of unpack what it means concretely. Concretely, a limit of F is an object X with maps here, commuting with all the maps coming from I. So that's just the datum of a cone over F. But it's supposed to be final. So any other cone will map to this one uniquely, such that so this is what it means to be final, such that for any other cone, let's call it, say, X prime, with its own maps, which commute, there's a unique map from X prime to X, which commutes with the pi i's. So let me draw it. Here I have the pi I prime. Here I have the pi I. And if you think of our example, say equalizer or pullback, this was exactly a universal property for the fiber product. So in this example, let's suppose this is X, Z, and Y. The fiber product this is a cone for this diagram because it maps to X and it maps to Y and then composing maps to Z. So this is a cone. And what we checked was to define a map to it was the same as to define a cone. A map to X, a map to Y that composed to the same thing on Z. So this was a cone, and we know it's final. We know all other cones map to it uniquely. So what does that mean? That means in this notation of a limit, I would say that the limit, I'll draw the functor just as a diagram because that's what it is. The limit equals the fiber product. Well, together with its data of projections. But as an object, the underlying object is just this fiber product. Okay? And the dual notion, I'll just write it because we're done. So, no, they don't have to be. And the definition makes sense in a general category. It might not exist. There might not be fiber products. But if they exist, they're the limits of diagrams of this sort. So dually, a colimit of f, if it exists, is an initial cocone under F. So just read everything backwards. There will be a map from f of I to this cocone, where everything commutes. And given any other cocone, this initial one maps to it. Okay? So the thing to remember pardon? I have a projection. You're asking what are the projection maps?
No, you wrote x to y, z to y in limit equals fiber product.
Oh, sorry. This is z, and this is y, like here. Okay, so here's the slogan to remember. We know how to map to limits and from colimits. And then bear in mind these examples. For instance, if fiber products are pushouts, ask yourself, do I know how to map to a fiber product or out of it? Do I know how to map to a pushout or out of it? Okay. So let's stop there. There'll be lots more examples in the seminar.
Is the same thing as initial?
Sorry?
Is the notion of cofine same thing as initial?
There's a notion of a cofinal diagram or a final diagram, and it's a related notion, but it's not the same. It's about you could have two different diagrams with the same limit or the same colimit, and this is what finality or cofinality is about. So you have some very complicated diagram. You try to reduce it to a simpler diagram with the same limit or colimit. But this is another story.
Is any diagram of shape, for example, commutative diagrams, are they diagram of shape?
Yeah, some shape, which you can see by drawing it.
Precise definition. A diagram of shape by
I is a category. Yeah, so the data in the category, objects together with morphisms and how to compose them, that's the shape. Mm-hmm.
Let's take the diagram. Consider its coordinates only. And suppose that we are likely that for limit these maps and injections, and for coordinates maps.
Let me stop this because I think this is a long question, but we will answer it.